Okay, sorry about the delay. Welcome to this seminar. Can you please bring more water? Okay, thank you. Yes, so my name is Alexander Ilin. I'm a professor of practice in the Department of Computer Science. And today I will be talking about hierarchical imitation learning with vector-quantized models. So this work was actually done by Kalle Kuenpää, and Kalle was advised by me and Joni Pairinen. But Kalle has done all the experiments. So the motivation of this work. Yeah, okay. So we are interested in building an artificial intelligence that can solve complex problems. And we believe that in order to solve complex problems, our agent has to be able to plan its actions on high level, building a high level goal of what it's planning to do. So, for example, if we want our agent to play Minecraft, then in order to survive in that environment, it's a good idea to use some of those tricks. So, for example, it's a good idea to locate trees, to start a house, to build a crafting table, to make a pickaxe, and so on. But those are really high-level goals, because the agent needs to learn how to execute low-level commands in that environment. So those are really high-level goals, and our motivation is that the agent would learn some abstract representations of its actions, so that it can plan on this kind of level, not on the low level of commands, but with this kind of goals. So this research is related to hierarchical reinforcement learning, and I believe that currently hierarchical RL is dominated by model-free approaches, such as, for example, the option-based framework or Hiero. This is one of the popular algorithms. And in that research, usually we have an agent that learns from scratch. So it's just, it acts in the environment. It has absolutely no experience at the beginning. It has to collect experience doing exploration. And typical tasks in the environments that are considered in many works is this kind of task where you have an agent, for example, an ant that is supposed to move around to find some locations, or it's supposed to push, let's say, this red cube over here. So in this kind of environments, we have kind of high-level goals, for example, going from point A to point B, or pushing an object. But the agent actually operates with low-level commands, such as, for example, motor control commands. So we have to really learn how to achieve those high-level goals. And some intuitive benefits of hierarchical RL. So why do we want to build a hierarchical agent? Is that perhaps if we build such a hierarchy, then training and exploration happens in more semantically meaningful action spaces. So we learn representations of, let's say, our actions, and those would be those would have some meaning. Another intuitive benefit is that if you have an agent that has a hierarchical structure, then it might be easier for the agent to learn a good policy. So, for example, in this environment, if we would have one level of hierarchy that would just so that the agent knows how to move, let's say, from point A to point B, then using this low-level kind of commands, we can actually explore the area of this environment. So we can actually navigate in this environment and explore unseen places. So those are the kind of the intuitive benefits. However, there is evidence that the observed benefits of the state-of-the-art hierarchical reinforcement learning agents can be mainly attributed to improved exploration. So there is this paper in which they took a non-hierarchical agent and trained it on the experience collected with the hierarchical agent. And the paper showed that this non-hierarchical agent could achieve performance that was almost as good as the performance of the hierarchical reinforcement learning agent. So the point is that if you give a good experience to a non-hierarchical agent, it can actually learn very good policy. So the benefits of hierarchical agents seems to be in better exploration. But in this work, we would still like to find some benefits except for exploration. So we really think that there could be some benefits rather than improved exploration. And so that's why we consider a setup when the agent cannot really explore. So it's given some trajectories by an expert that knows how to act in a given environment. And the agent needs to learn a good policy just looking at the expert trajectories. And we hypothesize in this work that the hierarchy can be beneficial if we want to solve complex tasks that require careful planning, in which you, in order to complete the task, you need to consider different alternatives. And this is the case in the environments that we consider. So for example, this is one of the environments called Sokoban. In this environment, we have an agent, and the agent is supposed to move those yellow boxes at the target locations marked with this red squares. And in order to solve the puzzle, the agent really has to plan its actions, because if you make a wrong move, then the puzzle becomes unsolvable. So you really need to like search and plan ahead in order to solve the puzzle. So we hypothesize in this work that these kind of tasks would benefit from hierarchical planning, from building a hierarchy of actions. So in our setup, we assume that we have some demonstrations, again, produced by an expert, which knows how to solve the task, but we have only low-level actions in those trajectories. So the agent is not given the high-level goals. We only observe how the expert solves the task, but we don't know what were the goals, what were the intermediate steps that the expert was doing. And the behavior of the expert may be suboptimal. So it doesn't have to solve the task in a perfect way, in the fastest optimal way, in the fastest way. So the environments that we consider are those 4 environments. So the first environment is called traveling salesman problem. Okay, so the idea is that we have an agent that is marked with a circle, and the task of the agent is to visit all the cities. So the agent starts from this black square, and it has to visit all the cities. So the green squares are the visited cities, and the red squares are the unvisited cities. So you need to visit all of them and come back to the starting position. The second environment is called sliding tile puzzle. So in this environment, you have probably played this game. So we just need to order those tiles from 1 to 24 in this 5x5 grid. In the environment called box wall, the agent must collect colored keys and open color matching locks to recover more keys until it finally reaches the goal cell. So we are supposed to collect this gem that is marked with the $sign, and in order to collect that, we need a blue key. But in order to collect the blue key, we first need to unlock the red lock. So we need to pick up the red lock and so on. And the Sokoban environment. So in those environments, you really need to plan how to solve the puzzles. So what would be the easiest way of solving these tasks? The easiest way would be just to train an imitation learning policy by just trying to maximize the probability of the actions taken by the expert given the current state. So we have just some policy network, we just do behavior cloning. Another simple alternative, maybe a little bit more complex alternative, would be to treat this task as an offline RL problem. So we have some data set collected by the expert, and we just learn a policy using that fixed data set. So there is no exploration. And we just use this data set to learn a policy that would generalize to new environments, to new implementations of new instances of this environment. So for example, we can use this conservative Q. We can learn a conservative Q function like in this algorithm called CQL. But what if we apply those to our setup, we see that this doesn't really work very well. So we cannot really solve the puzzles. So with behavior cloning, we can solve, like, let's say 82% of the Sokoban instances. So it doesn't really work. So in order to solve these puzzles, it seems that you really need to understand like the high level goal. For example, you need to know that in the traveling salesman problem, you need to visit all the cities one by one and then go back to the starting position. And we propose our approach of solving this task, and we call our approach hierarchical imitation planning with search, or HIPS. And our approach contains 3 steps. The first step is learning representations of expert trajectories. Second step is training a generative model of subgoals. And the third step is planning by search in the subgoal space. So let's go through these steps one by one. So the first step is representation learning of expert trajectories. So the idea of this step is that we have a sequence, an expert trajectory from our data set, and we want to represent each trajectory as a sequence of subgoals that is a sequence of states observed within this trajectory. So the intuition is that each subgoal should probably correspond to a meaningful high-level action. For example, moving one box to a target location in Sokoban, or visiting one city in the TSP problem, or moving one tile to a target location in the sliding tile puzzle. Okay, so this is our initial sequence, so the whole sequence, and we want to select just a few key states, such that we kind of, the key states is a kind of concise representation, is a representation of the whole trajectory. So this is, so in kind of on the high level, we think that our agent is really moving from one subgoal to another. And it may need several steps to move from one subgoal to another. Okay, so how do we solve this problem? Actually, this problem turned out to be very hard. And so in principle, it's a time series segmentation problem. And just a spoiler, just segmenting the trajectory into intervals of fixed k actually works pretty well if you tune k well enough. But this is a kind of a silly way of representing an expert trajectory. We want to do better than that. We want to actually find some more meaningful representations. And we have spent a lot of time trying to come up with a better way of segmenting those trajectories. And we have one solution that seems to work better than this simple segmentation. So the intuition behind our approach is that the subgoals that we want to identify should be preferably as far as possible from the current state, because this will probably lead to faster planning, more efficient planning, because we can kind of skip more steps and consider more distant alternatives. On the other hand, the agent should be able to learn how to reach a specified goal. So if the subgoal is too far away, then the agent might not be able to reach that goal. So it has to be not too far away. And the third criterion is actually that the subgoal should be possible to generate, because eventually we want to plan it in the subgoal space. So we want to be able to have a generative model of subgoals. So if we have subgoals that we cannot generate during planning, that those are kind of useless subgoals. So we propose to solve this, to formulate this problem, the segmentation problem, as a reinforcement learning problem. So one trajectory is one episode of training of our agent that I call a segmenter agent. So the segmenter agent starts with the first states of a trajectory, and it needs to select one of the future states as the next subgoal according to its policy. So the segmenter agent has this policy that selects one of those future states as the next subgoal. And in practice, we consider only the following age. So we just consider a fixed length window for like as alternatives for the next subgoals. So basically we have H possible actions, and the agent just has to pick one of the H actions. So for example, in this case, it picks this state, and then it receives the reward that is written in this formula. So the reward is the log probability of the actions taken by a low-level policy that tries to replicate the express behavior. So given the subgoal and the current states, we train a low-level policy that tries to reach that subgoal from the current state, from the expert data. And if the probability of the observed expert's actions is high, then the segmenter agent gets high reward. So the intuition is that we want to segment the trajectories into sub-trajectories such that the low-level agent trained as a simple behavior cloning agent can go from the current state to the next state. Then we have this penalty term alpha, because every time you kind of select the next subgoal, you have to pay penalty of alpha, so that we want to encourage the agent to select as few subgoals as possible, to have as few sub-trajectories as possible. Okay, so then the agent receives this reward, and it moves to the next state, so the state that is marked over here. And then again, it has H possible alternatives for selecting the next subgoal. It selects, for example, in this case, this subgoal, and moves, the state of the agent moves to the next subgoal, and we iterate this process until we reach the final state of the trajectory. And we train the segmentation agent using standard reinforcement learning algorithm. And the low-level policy, the policy of kind of the low-level agent, is considered to be part of the environment, and is trained together with this segmentation training of the segmentation agent. So it's kind of part of the environment. So it's updated all the time. So it's updated by minimizing this loss, which is kind of standard loss for training a goal condition behavior cloning agent. Okay, so that's the first step. Do you have any questions about the first step?
So,
yeah.
Is the fact that we're training the level policy together with segmentation agent kind of like in the environment non-stationary?
Well, I would say that this non-stationarity is kind of part of the environment. So it's kind of, you can think of it as this, that it's kind of stationary, but it's changing. The low level, it contains a low level agent that is changing all the time. Okay. Then the second step. So in the second step, we take the subgoals, those keyframes that we identified in the first step, and train a generative model of these subgoals. We use a generative model called VQVAE. It's a variational autoencoder with discrete latent codes, largely inspired by this paper from ICML 2021. So in our model, we take the current state and the next subgoal, and we use an encoder to encode those states. So we basically don't encode an individual state, but we encode the difference between the current state and the next subgoal. Then we use this. Then we use this code and discretize it like you do in VQVAE. And you pass this discrete code to the decoder, and the task of the decoder is to reconstruct the next subgoal given the current states. So again, the code that we generate here, it represents the difference, what you need to do to go from the current states to the next subgoal. Okay, and once we train this VQVAE, we can actually generate new subgoals conditioned on the current state. And the way how we do it is that we can generate this discrete code using the prior that we trained when we train our VQVAE, and then we just use this discrete code that we generate over here and pass it to the decoder that takes the current state and produces the next subgoal. So we can generate a variety of the next subgoals. So a couple of notes is that the number of possible codes is finite. It's just our like hyperparameter, how many codes we want to have in our model, which means that the number of the generated subgoals is finite as well, which is kind of good for the search methods that we use for planning. Another note is that different codes may actually result in the same generated subgoal. Sometimes it happens, and this is a kind of an expected desired behavior, because in some situations, for example, when you are very close to solving the puzzle, you don't actually have too many alternatives. So the number for the subgoal, so the number of codes can be too large for the puzzle that you are trying to solve. And all of these networks are resonance-based CNNs and with some film layers. Any questions about the second step? Yes. Yes. Yeah, so you try to predict the next subgoal. You skip the whole trajectory in between, just predict the next subgoal.
How exactly is this? So you take the current states, you have path between the current state and the next subgoal, and this decoder. So is the idea then that you take the state selection policy and then you run that over the latent codes? So you condition the state selection policy on the current state, you then evaluate the latent codes and you say which one matches like whatever.
So there is no policy as such. So we start when we try to solve a new puzzle, we start from the initial state,
right,
and we use our decoder to generate possible next subgoal. So where could we move from the current state as the first step?
okay.
Then we can repeat the same procedure to one of those child states, that we generated. And so we created 3. So I'll have a slide about that.
Yeah, so the goal of the segmenter agent is kind of to initialize the training data set for the VQVAE. So it's a training only, and we don't need it anymore during evaluation.
Yeah. Okay, and then the last step is high-level planning with search. So in this step, we just use standard search algorithms such as greedy best first search or policy-guided heuristic search or A-star or Monte Carlo tree search. And we perform planning in the subgoals space. So each node in our search tree or a search queue is one of the subgoals that is generated by our VQVAE. So we start with the initial state. We generate next subgoals using our VQVAE decoder, using one of the codes that we sample. Then we select one of the next steps according to our selection, like some heuristic procedure. And then we expand this node by, again, generating possible next subgoals if we want to move from this next subgoal. And again, we use the same VQVAE for the subgoal generation. And in this work, we assume that we know how to detect the terminal state. So we know when the puzzle is solved. So we can just do a search. And then once we find a solution that solves the puzzle, we stop the search. That's one possibility. So this is just a pseudocode of what happens in our search procedure. So it's very simple. We just take the node from our search queue, which has the highest priority according to some heuristic. Then we just expand it using our VQ-VAE. So we create those nodes. If one of the nodes is a terminal state, we quit. Otherwise, we just insert those nodes into the priority queue using our kind of priority function. One of the it may contain some heuristics. So those different algorithms, such as the ones that I mentioned here, so GBFS, PHS, or A star, they are different in the way how we use, what kind of heuristic we use to prioritize different nodes. Any questions here? Do you understand the idea, Marcus?
Well, I have a meaningful question. So there should be no reward. But is this prediction kind of like an implicit?
So there's no reward here. We just try, and in the expert trajectories, there's no reward. We assume that the expert only gets the final reward when it solves the task. So we assume that we know how to detect the terminal states when the puzzle is solved. That we assume to be known. Kind of we know the reward function basically. It's mainly 0 but 1 once the puzzle is solved.
But I mean, could you interpret the subgoals as rewards?
I don't know, maybe, but I don't see how to use this in practice.
Like you could technically learn about function. Having it for the state of solving it even a certain that would be a way.
Yeah, so we learn a value function and we use that like in the heuristic. So when we have this get priority function, so we use in there we use that word value function. And in theory we could learn a reward function, but that would kind of change the setting in which we operate with the imitation learning setting.
I mean, so do we assume that when the imitator and we observe stuff, we know that assume that stuff we observe is full?
We don't assume that we assume that it's somehow satisfiable, so we kind of reach this sum goal, and we don't assume necessarily that it's anywhere close to optimal, but it still ends like in a successful terminal state.
Yeah, so we assume that it makes sense, maybe not optimal, but it makes sense. It's something that seems to be successful in the past. So like my high level goal is that what if we create this experience by ourselves and randomly like collect some reward? Can we look back at our experience and try to kind of figure out what did we do well? What kind of sub goals, what kind of subtasks did we complete in order to achieve this reward? So hopefully we can extend it in future work also to include exploration, and maybe we can learn from our own experience.
I guess basically it's some data that you find from that the exploration is already done.
Yeah.
So you've explored the entire state space.
Yeah, approximately. Sometimes we actually run into problems when the exploration and the expert data is good enough. Right?
But then you just something. Yeah.
Okay. So now the experimental results. Yeah, we consider these 4 environments. And first, I want to visualize some of the sub-goals proposed by VQ-VAE during planning. So this is one of the intermediate states that was proposed during planning. And those are the states, the next sub-goals proposed by the VQ-VAE as next possible sub-goals. So you see that the agent is currently at this city, and different sub-goals correspond to visiting one of the unvisited cities. And in order to reach any of these subgoals, the low-level agent has to perform actually multiple steps. But we skip those steps and we immediately think, what could be the next city that we could visit next? So I must say that in this particular environment, there were two modes, like two solutions that our segmenter agent was finding. This was one solution that kind of has very nice interpretation. There was another solution when the agent was just next to the next unvisited city, so one step before. And but the VQAV was able to kind of generate those subgoals nicely, and we could do planning, even though like the interpretation was not as good as here. The method still works. For other environments such as Sokoban, this is the same visualization where in this state, and those are the subgoals proposed by our generative model. It's kind of less intuitive what the model is doing, but my interpretation of those subgoals is that the high-level agent proposes to move the agent from the current cell to one of the empty cells that you see in the environment, and you may push one or no boxes on the way. So either you push one box or no boxes, and these are kind of the subgoals proposed by the high-level agent. This is an example of a high-level plan. So the plan that our agent found during a search, so as a result of the search. And you can see the agent nicely travels from the starting position and visits all the cities until it gets back to the starting position. And I guess in this experiment, we also wanted to optimize, like minimize the number of steps that the agent does. So that's why the behavior kind of looks actually quite good, close to the optimal behavior. This is one example trajectory for Sokoban. So this is the starting point. Yeah, I'll move this. I'll use this one. So this is the starting point. And I guess first you kind of just move the one of the boxes to let the agent free, so that it can move. In the next subgoal, what happens? I think it pushes this box over here. Then in the next subgoal, it pushes, I guess, this box over here. Then it continue pushing this box, and it ends up here. Then it pushes those two boxes here, and finally, once it's in this state, it's very easy. Just it knows how to push those two boxes to the target location. So this is the high-level goal that was generated by our agent. This is just an example for sliding tile puzzle. Again, this contains more high-level steps, so you see that, for example, it takes two sub-trajectories to move the first tile 24 to its target location. So it actually has multiple steps when it tries to move one tile to its target location. Okay, those are the success rates in solving the puzzles. And you can see that our agent was able to solve a much higher ratio of the puzzles. So it's doing much better than the behavior cloning agent. Maybe except for the box world environment, where the problem was that it was not able to learn a good low-level dynamics model, because when we do the search, when we create a new subgoal, we try to evaluate whether that subgoal is reachable. And in order to do that, we learn this dynamics of the environment. And in the box world, we just didn't have enough transitions to learn a good model in the expert trajectories, because the experts, I guess, were not doing very stupid things. So it was actually very hard to build a good model. But once we have access to the world, to this low-level world model, so this is the version called HIPS-env, you can see that we can basically solve the box world as well. So there is one method called K sub S, which was published at Nearest 2021. On the high level, it's actually very close to our approach. But in that method, it splits the trajectory into intervals of fixed length K, and then it learns another generative model of subgoals, but they use like an autoregressive model of subgoals. And it seems that our approach works better in these environments. So on this slide, we compare our approach with some alternatives. We display the success rates, like how often our agent solved the puzzle after performing n node expansions, because the promise of this hierarchical planning is that we can actually build a much smaller search tree in order to find the solution, in contrast to kind of low level search that requires building a very large tree. So for example, this PHS star is a kind of low level search where you search for you try to solve the puzzle using the low level actions without kind of any high level planning. So you can see that, for example, for the sliding tile puzzle, our agent is able to solve many puzzles with this, let's say, with 100 node expansions only, and low level search is not able to solve any of those puzzles. In this table, we compare our method with heaps K, which is a version of our method where we don't have the segmenter agent. We just split the trajectory into intervals of fixed length K. And here we actually tuned K carefully, so it wasn't like just some K, but for each environment we tried several Ks and we found the one that we used one K that works best in this environment. And you can see that our segmenter, like our way of segmenting the trajectory, works slightly better because we can we can solve the puzzles much faster using fewer node expansions, so it works better. On this slide, we actually wanted to show that you can use our method and improve and find better trajectories, like better solutions compared to the solutions that you see in the expert trajectories. So for example, in the traveling salesman problem, we assume that we want to minimize the number of steps in order to solve, like to visit all the cities. And our teacher, the expert that was creating the demonstrations, it actually selected the next visited city in completely randomly. So it visited city in a random order. And on the average, it used 336 steps to go through all the cities. But when we use our method for planning, we can actually visit all the cities much faster with much fewer steps. And so this, for example, this Christophidis is one of the algorithms that like can find a solution that is very close to the optimal solution. And you can see that our solution is very like kind of quite close to the solution that is very good. Okay, so that was the last slide, and so this work is just a baby step towards learning abstract representations of experiences. So we really want to kind of build the learn representations of actions or experience, and we believe that this will be very useful for AI, and this work can be extended in multiple directions. For example, we can combine this high-level search with low-level search, because if our generative models, let's say, is not good enough, sometimes we are not able to generate good subgoals. And in that case, it might be a good idea to try low-level search so that we can actually plan on the low level. And it might be a good idea to combine the high level and the low level search so that we have like the convergence guarantees of the low level search, but we have the speed of the high level search. Of course, learning representations for high-dimensional sensory inputs, such as like images or videos, and using continuous actions. That would be a nice direction for future research. Another important direction is that is kind of formulating the goals such that we can ignore distractors or irrelevant observations, because right now we formulate the goals, the sub-goals in the observed space, or in the observed space. So if there are distractors like irrelevant agents that we have to ignore, it might be difficult for this approach. So it might be a good idea to solve that problem. Again, adding exploration and kind of using this kind of agent, hierarchical agent, when learning from scratch might be a good direction for future research. And one interesting direction that I also like is that can we kind of correlate those high-level goals with, let's say, language instructions. So for example, if you're given an instruction, like the agent is given an instruction in natural language, can we actually find representations of the trajectories that are kind of correlate with language instructions, so that kind of the agent understands the meaning of those language instructions? So can we kind of learn from, let's say, large language models or from language and combine these approaches? Okay, so that was the last slide. Thank you.
So we have time for questions.
Can I ask one actually about the policy, the selection policy? It was the very first step. So what's an example of a trajectory? So like when you were learning this policy, you have you kind of have this inner loop where you learn like a behavioral learning policy based on like how easy it is to get to this target state. So what's an example of a target state that would be difficult to get to with the behavioral learning policy, and what's an example of a target state that would be easy?
Okay, so I believe that if we look at this table, so if I believe that if we give our low-level agent the final states of the trajectory, it's probably very hard for the agent to learn all the steps in between. I don't know, because it's kind of too far away. But the one that is very easy to reach would be the next, I guess, the next state, because that one would be very easy to predict what to do.
Is it that you run this in a loop for a fixed number of iterations? Basically, like you try to learn this behavioral policy learning every time you want to select the next thing.
So we run just once. So we run the segmental, we have one trajectory, we run the segmental once, and then we run the overall once. And then we move to the trajectory.
Right, but what I'm wondering is like when you're selecting the next stage for the segment, the criterion is based on how well you can reach the next stage given the subgoal. Like how well you can reach the subgoal is the behavioral learning policy. And so do you retrain that from scratch every time, or do you just have this behavioral learning policy that you train using some random selection, something or whatever?
So we train them like short. Okay. So we do not reset the low-level behavioral forming policy, but we continue to update. Right.
Do you think that this point in hierarchy strength or weakness towards versus like when you first, for example, the low-level policy on 10 random chance, and then this is meant to already training?
Actually, what we do is that we initialize the low-level by training.
Right.
Because it's probably mostly
Yeah, and it includes that. And then you kind of find the low-level policy.
Right. I guess that visualization is actually important, because otherwise you end up with this kind of non-stationary. Like I know that the policy is part of the environment. You know, like that's in theory that makes the non-stationary go away, but yeah. Or at least I remember when we were looking at something kind of similar to a few years ago, like we were having kind of similar problems with sort of the problems. And then the next question I have actually is, was the test data like a different, was the test data a different distribution of states compared to the training data, or was it basically like?
Then we are handling like RL problems during some like from a gene environment. Okay, so it's the same distribution. But obviously like unseen.
Okay, yeah, so unseen states. So your VQVA can propose the subgoals for things that are in your sort of validation split, right? It's like the same distribution of states, but they might not necessarily be secret.
Probably not.
Yeah, another thing is about the variation of the latitude and leaves and how does it work?
Yeah, so the question is, what's the difference between heaps and heaps env? So when we build this tree, we take a node and then we do the node expansion by generating subgoals with vqve, and then we make sure that each of those nodes is actually reachable. So this is not something that cannot be reached. So we actually run in the version that is called heaps, and we run the simulator of the environment using, I guess, the low-level policy, and see if it reaches the goal in a certain number of steps. If it doesn't, then it's a non-reachable state, and we don't include it. And in the version without env, we actually learn a dynamical model of the environments, and we use that one to see if the state can be reached or not. Okay. So we don't rely on the simulator. Yes, so the biggest difference was in the box world. I guess Kalle knows the best what was the problem.
Yeah, in the expert data, we don't have examples of like the expert trying to open the lock with the wrong color key. So it doesn't learn the connection that it needs to open the key with the right key of the right color. So it's sometimes the dynamics model thinks that it's able to open this lock even though it's not. And that leads to the difference.
Whatever key or
you need to have some kind of key, but it doesn't ignore the color of the key.
Lauri, please.
For example, if the expert code guarantees or textual from turning somehow you have to spend go somewhere we should be aware if that happens today. That's something we have a finite fusion horizon for selecting some code. If that's somewhere in the room, you might not be better able to break but
it might happen, although what we observe in practice is that even though those subgoals, that they don't have this clear interpretation that, okay, now we go actually and push that box, even if the agent goes around, it might just select like some intermediate steps as possible subgoals. But I don't know, I think we didn't have very bad expert trajectories.
In theory, I still think we didn't evaluate but in theory they should be able to handle that because we have the VQVA and the circular speaker. So in theory the value function should learn to output very bad value estimates for those kinds of misdirections. But on the other hand, the value function was also trained using the expert data. So yeah, but of course, because we are doing the search, we are at least noticing that this kind of misdirection.
And this is sort of like an extent between behavioral coding and offline behavioral learning, right? cloning, if you have these bad expert trajectories, you'll just blindly copy. Whereas in offline reinforcement learning, you're going to be keeping track also of the rewards in which the expert is getting into different trajectories. And so therefore, if you condition on sort of saying, you pick optimal trajectories, you're going to implicitly filter out those things which that. Right? And I think you'll basically end up doing the same, right? Like you're proposing sort of these different states that you can go to, and you already have this sort of, I don't know if it's in the heuristic function or whatever. Basically, some states are going to be labeled as bad, and other states are going to be good. And if you're always the good ones, then you're fine.
Yeah, and for that we have like the third party, like case bar. So we are keeping like track of the number of steps used. So if we go very far in the bad direction, we're not just going to expand those blocks because they have a low priority.
Okay, but let's close this session. Let's try to figure it out.